Hi everyone, thank you for tuning in to a short explanation to learn about FHI-aims, an ab-initio material simulation package for materials science and chemistry. FHI-aims is a command line program that takes in text files and outputs data as text files. Starting a calculation requires only two key and mandatory input files: a geometry.int file that contains all structure-related information, and a control.int file with the computational settings. Both are just plain text files you can create and manipulate with any common text editor. Let's look here at the example of a water molecule. I've already created the two input files, so let's take a look. The geometry.int file follows a very straightforward syntax. Each line in here represents one atom, 2 hydrogen and 1 oxygen atom in total. Each of these atoms are defined by their Cartesian coordinates given in units of angstrom. The atomic species is indicated at the end of each line. The next file is the control.int file, which then actually controls the simulation with FHI-aims. In it you put any parameters that specify runtime choices and the numerical settings of the calculation. Let's say here you want to run a very simple DFT calculation with a PBE functional. We start by including the exchange correlation functional, here PBE, the first line. We have the relativistic approximation, in this case relativistic atomic Zora scalar, which is our recommendation to obtain consistent observables across all simulations. And we want to do only a spin non-polarized calculation. Next up, we need to define the actual numerical settings, and these include the basis set. FHI-aims uses numeric atom-centered orbitals as basis functions. With the FHI-aims software package, we also ship predefined defaults for every chemical element that you can append directly to the control.int file. These defaults come in different flavors and levels of accuracy. Our NAO basis sets range from light, intermediate, tight to really tight settings. More accurate species defaults also lead to higher computational cost, but more accuracy. So we recommend in general to always check the accuracy of your simulation by comparing different default tiers. It's always necessary that the species defaults in the control.int match all the species found in the geometry file. So please keep this in mind. The species defaults can be found within the FHI-aims folder under species_defaults, where the current NAO templates are stored in defaults_2020. Now that we've created the geometry and control.int files, we'll try to run a simple calculation with FHI-aims. We still need to append the species defaults for our water molecule, so let's do that now. For this demonstration, we'll just use the light species defaults, but feel free to also try out the other ones. So we just append here, with the cat comment, both the species defaults for hydrogen as well as for oxygen to control.int file. Then just quickly check again that everything worked out correctly. As you can see, we both now have hydrogen and oxygen species defaults within the control.int file. Next, we can actually start the calculation. Go back to the command line, run, in this case, the MPI run command with 4 cores, because FHI-aims is MPI parallelized, and append the result to an aims.out text file. The output stream in this case will thus be written directly to aims.out. This should only take you less than a second, and then you can check the calculation by opening the aims.out file once it's done. If you scroll all the way down to the end, you will hopefully see a "have a nice day" to indicate that the calculation successfully ran. So I can only say congratulations, this is your first FHI-aims calculation. As FHI-aims can seamlessly simulate molecules and periodic systems on the same footing, we can also look at the slight differences for a periodic system. So this is the example for a silicon bicrystal in a primitive diamond structure. As you can see, the geometry file now starts with 3 lattice vectors, and these 3 lattice vectors define the unit cell. Once again, the lattice vectors are also given in units of angstrom. Next up, we define the positions of the 2 silicon atoms. But notice that we now use fractional coordinates given by the keyword atom_frac. You can also default to Cartesian coordinates, as in the molecule example, but just make sure not to mix Cartesian and fractional coordinates in the same file. The control.int file, compared to the previous case, only features the addition of a kgrid keyword that is needed to properly sample the reciprocal lattice of the periodic system. FHI-aims geometry files can of course be visualized with several graphical programs, like Vesta, JMOL, XChristen, among many others. We also develop a graphical interface for material simulations, or GIMS for short, that directly deals with FHI-aims files. With GIMS, you can visualize structures, create control files, and even analyze the output files after any FHI-aims calculation. A full description of possible keywords you can use in both the geometry.in and control.in file can be found in our manual. If you're more of a hands-on person, you can also try out our online tutorials that illustrate most of the common use cases, such as structure optimizations, electronic structure analysis, to even more advanced topics like spectroscopy, thermodynamics, and more. If you want to start using FHI-aims for your research, please have a look at our tutorials. The list is always growing, and we hope to ease your way into using FHI-aims as much and as easily as possible. For more examples and in-depth explanations, please check out our website and online tutorials. Happy simulating!